Hi everyone. In this video, we're going to talk about removing discontinuities. So we've already learned that a point discontinuity is also considered removable. So in this video, you'll after watching the video, you'll understand why we can call a point discontinuity removable. But let's start by looking at this graph, which represents f of x. And let's just start evaluating some limits. So first we want to find the limit as x approaches -1 from the left. So as x goes to -1 from the left, y is approaching 1. Okay, let's find the limit as x approaches -1 from the right. So hopefully you notice that y is approaching 1. So that means, since our one-sided limits are the same, that our two-sided limit also equals 1. Okay, now let's try to find f of -1. Well, f of -1 is undefined because we have an open circle, which is the reason that this graph is not continuous at x equals -1. But think of it like this. What y value would patch the hole at x equals -1? Like if we were able to redefine f of -1, what would it have to equal in order to fill the hole? Well, I hope you're seeing that it would have to equal 1. So if f of -1 equaled 1, then this function would be continuous at x equals -1, and we would have removed the discontinuity, okay? So removing a discontinuity, you can think of it as like patching the hole, okay? But you can only patch a hole for discontinuities that occur where a limit exists. Because remember, in this example, the limit did exist, okay? So discontinuities that occur where a limit exists can be removed by defining, or in some cases, redefining a point on the graph. You guys, I also think of a removable discontinuity as, sometimes we refer to discontinuities as removable or non-removable. So like a point discontinuity is removable because if we can just define or redefine a point on the graph, we can remove the discontinuity. But we wouldn't be able to do that with a jump discontinuity or an infinite discontinuity. So those are considered non-removable, okay? All right, let's look at some examples, okay? All right, so here's an example. We're given a piecewise function, h of x, and we know that h of x equals x squared minus 7x minus 18 over x minus 9 when x does not equal 9, and h of x equals k when x equals 9. And we want to figure out what value of k would make h of x continuous, okay? Well, remember, k would have to equal the limit, okay? Because right now, like if we went through our definition of continuity, and we started at step 1, if I evaluated f of 9, based on the way the piecewise function is written, right now it equals k. All right? If I go to step 2 and I evaluate the limit as x approaches 9, well, Well, remember, with this type of piecewise, to evaluate the limit, we're interested more in when x is not equal 9. Okay, so to evaluate the limit, we're going to use this function. And we're going to try direct substitution first, but we're actually going to get 0 over 0. So that leads me to trying factor and cancel. But remember, 0 over 0 does not mean the limit does not exist. It just means we have more work to do. So let's try factoring the numerator. Factors of -18 and add to -7. Looks like -9, +2 would work. And then x minus 9 over x minus 9 simplifies to 1. So I'm left with the limit as x approaches 9 of x plus 2. Now I can just use direct substitution, and the limit equals 11. Okay, so remember our third step. In order for the function to be continuous, the limit has to equal the function value, right? So the limit as x approaches 9 of h of x has to equal, and I should have made that h, sorry about that, has to equal h of 9. Well, we know what the limit equals, right? That equals 11. So k has to equal 11 in order for this function to be continuous, okay? So like if the piecewise was written like this, where k is 11, then that function is continuous when x equals 9. All right, you guys. Sometimes instead of that type of piecewise, you'll be given a piecewise function where you have inequalities. But again, the question is the same. Find the value of the constant k that will make the function continuous. Okay. All right. So remember that in order for the function to be continuous at 2, the limit as x approaches 2 of f of x has to equal f of 2. This is just the third statement in our definition of continuity, okay? All right, well, to evaluate the limit, does it make sense that we would evaluate our one-sided limits, and so we would plug into both pieces? And to evaluate f of 2, we would just plug into the kx squared, because that's where x is greater than or equal to 2. You guys might remember, when we did some practice in class and we had questions where we were trying to determine if a function was continuous at the point where the function changes, like the shortcut method was just to plug into both pieces. That's exactly what we're going to do here. We're going to plug in 2 to both pieces, okay? And then that'll give us an equation in order to solve for k. So if I plug in 2 into the kx squared for x, I'll get k times 2 squared, okay, equals, and if I plug in 2 for the bottom, I'll get, well, k times 2 minus 6. But I'd probably rewrite this. 2 squared is 4. I'd probably rewrite that as 4 times k equals 2k minus 6. And then notice you're just left with an equation, so you solve the equation, subtract the 2k, 4k minus 2k is 2k equals negative 6, divide by 2, and we get k equals negative 3. So again, there's basically, we're kind of using our little shortcut method where you're going to plug into both pieces. In the past, we would just plug into both pieces to see if we got the same thing to determine continuity. Here, because we're trying to find k, we're still going to plug in 2 for x, but we're going to be left having to solve for k. So the idea is the same. Okay. more example. Now, sometimes you'll be given a piecewise function that instead of having 2 pieces, it actually has 3 pieces, okay? And notice that it asks us to find the values of a and b that would make f of x continuous. So in this case, we are going to plug into all 3 pieces, okay? So I would start with, so notice how we have a 0 here and we have a 0 here. We need to make sure, in order for the limit to exist, okay, we basically need to make sure that our one-sided limits are equal to each other. Because that would mean our two-sided limit exists and is equal to that number, okay? So if I were evaluating the one-sided limit as x approaches 0 from the left, I would be looking at this piece, because if we're approaching 0 from the left, x would be less than 0. Okay, so because that's a constant, I know the limit's going to equal the constant, so that's just going to equal 2. Okay, the limit as x approaches 0 from the right. Now, if I'm approaching 0 from the right, those values are greater than 0. So in that case, I would plug 0 into the ax plus b. So I would get a times 0 plus b. Now, luckily, this just works out to 2 is equal to b, because a times 0 is 0. Okay? All right, now I have to also do the same thing with the 5. We want to make sure the limit, you know, in order for it to be continuous, the limit as x approaches 5 from the left of f of x, we would need that to equal the limit as x approaches 5 from the right. Okay, so again, if I'm evaluating my left-hand limit, x would be less than 5, so I would plug 5 into the ax plus b. So by plugging 5 for x, that's going to give me 5a plus b equals, okay, to evaluate the limit as x approaches 5 from the right, that means x is greater than 5, I'm going to plug into the negative 3x plus 7. Okay, so notice I'm going to end up with an equation in terms of a and b. But that's okay because I already know what b is equal to. So eventually I'm going to substitute that and we'll be able to solve for a. So now I'm going to substitute the 2 for b. And now I can just solve for a. So I'm going to subtract 2 from the negative 8 to get negative 10, and then I'm going to divide by 5 and get a equals negative 2. So we have a equals negative 2 and b equals 2. We solve for a and b. And so these are the values for a and b that would ensure that f of x is continuous. All right, you guys. So we're going to stop there with this video. And we will definitely practice this in class tomorrow. But as always, thank you for watching and have a good night.